Hello everyone, thank you very much for your kind invitation. The objective of today's talk is to give an overview of the research that we've been doing in our team in several areas regarding to artificial intelligence. So I have lots of slides. Fortunately, you cannot see the counter exactly. So, I'm telling this because I think I will make it in a specified time, but I would prefer to have your questions at the end, if you don't mind. I think it will be easier for me to meet the schedule. A short information about me. I graduated from the University of Science and Technology, Artificial Intelligence. Then I started, as I was a little bit upset by somehow limited education, I did my master's in arts in Jagiellonian in philosophy, which was kind of fortunate because later on they invited me to contribute to the cognitive science program, and somehow I've been also working in Jagiellonian for several years now. You can find more information about my research team, which is a team in artificial intelligence and intelligent systems on this website, and now I'm enjoying this nice stage when I finish some paperwork regarding my work, and I'm trying to find some interesting new topics that are not necessarily linked to what I've been doing earlier. So what I mean by these new topics. So currently my work is on the intersection of knowledge engineering, so what I've been doing previously, affective computing, and this is one of the areas that I cooperate with my colleagues here in the Institute of Physics, and also more recently explainability in artificial intelligence systems. Ultimately, what we would like to have in several years, hopefully, is to build intelligent systems that understand and use information and human emotions. And basically what we mean by these machines, we mean, of course, computer-based systems, but what is important is the integration of hardware and software. With hardware, we are mostly focusing on mobile and wearable devices, especially wearable sensors, so hardware that can be constantly with the user, as well as some intelligent infrastructures in the so-called, like, for example, in smart buildings. So this is commonly referred to as ambient intelligence systems, and by software we mean adaptable software that can that is designed in a human-centric fashion, and then is very much interactive and, as I mentioned, adaptable to the needs of individual users. And in order to build this kind of solutions, we are combining different artificial intelligence methods. So on one hand, we of course use data mining and machine learning to get a hold of the data that we get from the sensors. But on the other hand, as we care about understandability of the system to the user, we are also using these symbolic methods for knowledge representation reasoning, because thanks to them, a user can also more knowingly interact with the system. So in a way, as I will develop later on, we are building a special, from our perspective, we are building a special kind of decision support systems tailored to the needs of individual persons using them. These systems are commonly referred to as, for example, smart advisors or cognitive advisors. So these are just like catchy names if you're applying for projects, but in general I would call them just decision support systems, and they are they've been recently developed in this so-called context-aware system paradigm that I will come to later on. And in our opinion, affect, so information about the emotional condition of a person, can be this important additional dimension of context. But before I talk more about this, I wanted to come back a little bit to our original work and our background, which is still very much useful and relevant in this area. So this is what is commonly referred to in artificial intelligence as knowledge engineering. So a very short introduction, so you all have some intuition what we are talking about. So again, knowledge engineering methods are commonly used in decision support systems. Decision support systems have different realizations. So today, very often we mean by them a recommendation system. A recommendation system would be also a personalized one. So if you're, for example, so there are of course some, let's say, smaller applications. If you look for some like classic applications of recommender system these days, you can think of like the biggest companies supporting is Netflix. They live because of AI-driven recommendation system, or Amazon. So sometimes recently decision support systems are more considered in a so-called business area, whatever it means, but basically they've been around in artificial intelligence as decision support from the very beginning. And what is important for us is that they use certain models of knowledge to operate and to make these decision support. And these models of knowledge, they capture expert human knowledge about some specific domain or about some specific problem. And what is important is that these models are transparent and understandable to the experts, and then maybe in some cases, if this is also needed, to the users. On the other hand, these models are interpretable. We usually call it automatically interpretable machines, and this is why we talk about these automated reasoning systems. So usually they are described on some symbolic level. Very often they use some kind of logical language, and this is why a machine-based method for reasoning can be provided. And so basically you could think of them about as some kind of symbolic languages for knowledge representation and knowledge handling. And KRR, so knowledge representation reasoning, is one of these classic areas of artificial intelligence. Some of you might know this not so nice nickname of good old-fashioned artificial intelligence. So even though it was proposed in the good old-fashioned years of AI, it is still very much relevant. And recently, if you go to some machine learning conference, they would tell you, oh, we really need to incorporate expert knowledge to know what is going on in the deep network somehow, which is kind of interesting. So anyway, as we said, this kind of methods usually model human reasoning, which supposedly should be rational. This human reasoning is modeled here as a kind of logical inference, and in a way, this logical inference can be formalized during using some kind of logical language. So this knowledge engineering process, which is described in the textbooks in this area, usually involves acquisition of knowledge from the human source, or maybe from some other textual sources, etc. Conceptualization of knowledge, then formalization, some knowledge representation language. What is really important is the evaluation of the knowledge base to have some kind of idea about the property of the system, if it will operate in, for example, deterministic manner or indeterministic manner, or if it is a complete specification, etc. And then the actual execution of the system to get the decision support, basically. And so we did quite a lot of work in this area with my team, just to give you a glimpse. So the overall approach that we developed is called Semantic Knowledge Engineering, and this has been in the works for about 10 years and had many different branches that I will mention in a minute. And the core of it is a special kind of knowledge representation method that we developed, which on one hand is a symbolic language for knowledge representation. It is a rule-based language. On the other hand, for the design purposes, it combines decision trees with decision tables, so it is like a decision network. So if we start with this very basic example of a recommendation system, like maybe for Amazon, if you think about a system that is supposed to recommend a book to a certain kind of user, we would describe the profile of this user using some attributes. Then we formally, in this approach, we formally define the domain of attributes, and then having this specification, we write certain rules, okay, capturing the specificity of a certain user. So, for example, for some young persons who also like reading horrors, maybe they belong to a special kind of readers. So we might have number of these rules. In practical systems, the number of these rules, depending on the expressive power of the language, they can be from hundreds to tens of thousands. And what we try to address is how to manage this complexity, and this is what I will show next slide. And then we consider this as a dynamic system. So we say that the attribute values in a specific point of time define the state of the system, and then firing of a rule or a sequence of rules would contribute to the transition of the system to another state. And of course, this is a logical reasoning process, although this kind of logic that we are using here is, let's say, specifically tailored to this application. But of course, if you are a designer of such a system, you usually don't like to write such a thing by hand, especially engineers have some kind of let's say, distance to stronger mathematical formulation. So this is why we support visual design of such a rule base. So basically, one rule as this corresponds to one row in this table. And these tables group rules that work in the same context, in the same situation. Basically, they share the same attributes. And here what you see is a tree, but in general, this would form a decision network. Okay, and this is much nicer for the design purposes. And what is also useful from the practical point of view, that having this specification, we developed tools that generate, let's say, an executable format for a rule engine that we developed. So to summarize, on one hand, you have a formal specification of a decision support system and for modeling the domain knowledge, but for the modeling itself, you're using a visual support tool, which is much useful for the practical reasons. And the transitions between a formal model, a visual representation, executable model are formalized again, so you have kind of guarantee that it will match. And this is a very big picture that I could talk about for like 20 minutes, so I will do like in 30 seconds. So basically, we developed a design process, identifying number of design phases from conceptual modeling, logical specification, and physical design. And on each stages of this process, you have some specific languages for modeling of knowledge, and you have some tools that support these phases. Okay, so this has been a work of, I don't know, considering all the students and PhD students, maybe like 20 people or 25 people in some 10 years or whatever. So we have a number of papers about it, but what I showed to you is here. So this is this logical design. Okay, there are a number of ways to actually conceptualize this design, and then there is the executable part, which now in the next project that I will show to you, it's quite nice because it can run on your mobile phone. Okay, so this is how it is connected to the affective computing on the mobiles. And we have a number of papers in this area, and we had a project, NCN project, some years ago related strictly to this, and this resulted as in at least 2 PhDs, the PhD thesis that I supervised, and fortunately they were also supported by Preludium projects from NCN. And as we also tried to, let's say, stay close with the industrial reality, we had a nice project from Program Badań Stosowanych with a company, and in this project we actually addressed a much larger scope, because there is a thing that I completely omitted from here because I believe it's not interesting for you, in business process management. Okay, so in some other work, we demonstrated how these models can be integrated with this so-called business process management system. So one of these, the thesis was related to this one, and in this project we had business processes integrated with decision rules, with formal ontologies for conceptualization of business vocabulary, recommendation, adaptation, some number of these things, and it was a quite interesting quite interesting experience how a university cannot handle a large industrial project. Anyway, so most of it for me is fortunately like a closed story, so I can move on, and if you're interested in this, I can, for example, leave a copy of a book to Professor Nowak. Most of these things are described in the book that was published a year ago, and basically there is a part which describes the state of the art in much more detail, with the knowledge representation paradigm itself, knowledge engineering, and the selected applications that I was interested in, so the so-called business rules approach, business process management, semantic web, context-aware systems that will be related to affective computing, links of this whole methodology to software engineering, general programming approaches, and then there is this part about the formalization of these models, because I showed to you just the main model actually, but there are some other models that accompany this one in a larger scope, and then there is the whole part about applications of this approach in these different areas of computer science, basically. Even though I tried to somehow move on to the affective computing thing that I will mention now, we recently acquired a project in this GSTIRA, EU GSTIRA scheme, so it is like a special kind of call, which is like a combination of FET and ERANET, and together with University of Bolzano and Universitat Autónoma de Madrid, we will be working on developing method for understanding a semantic gap between what you get from the sensors and what you have like sensors in this Industry 4.0 setting, but actually it could be also applied to our affective computing thing later on, because it's just about sensor data, raw sensor data, and on a high level you have some kind of specification. In this case, again, it is a business process. And we want to demonstrate why differences appear and how to explain these differences to both the management as well as maybe the designers. And somehow a funny thing about this project is that after almost 20 years working in AGH, it's my first project where there is actually coal mining in it, because a colleague of mine from the other apartment, and our main use case so far is in real coal mining. And this is funny when she introduces herself, because she would say, okay, I'm working in data mining in coal mining. So anyway, but what matters mostly in this project for me is that we will have opportunity to work with some interesting people and really top teams in this area. So anyway, coming back to the bigger picture, you might ask yourself a question, okay, you have these nice decision tables, thanks to our representation, which is quite powerful in terms of expressiveness. The good idea is that maybe you don't need tens of thousands of rules like a classic rule-based systems, but maybe only hundreds of rules. But hundreds still doesn't sound maybe so nice, especially if you were supposed to write it by hand, and especially if these rules somehow are connected to your sensor data, and this sensor data can change. So the question is how to develop or update the knowledge base in a somehow smart, whatever it means, and definitely personalized way if you want to somehow meet the requirements of individual users. And this context-aware system paradigm in artificial intelligence comes to hand. So very short introduction what we mean by this, using on one hand, let's say, kind of explanation, and then using a hopefully persuasive example. So if you looked in the papers, basically they would tell you that context is the information that the definition that I like most is that context is any kind of information that can be, which is kind of useful to characterize situation of a given entity. So this entity, usually, in our case, usually it is a person, okay? But on the other hand, it can be a device, it can be a robot, it can be a machine, maybe in a more restricted case, it could be your mobile phone. And then this awareness is mostly related to the possibility of the system to select and restrict the knowledge it uses to make a decision support, okay? Because usually, especially these days, we have too much data. Maybe we have still, even in some cases we lack knowledge, in the other we have too much knowledge, and the question is, which is the relevant and most useful knowledge source in a specific situation to make the decision support? So this is this awareness thing, and the systems that use it, this approach, are many of these applications that you can see here. But just to give you an example, imagine that for some reason you are putting these two keywords in Google. But what is important, you are putting it in Google in your mobile phone, okay? In your mobile phone. And then the question is, what do you get? So there is a good chance that you will get this, so information about a celebrity. But maybe what you actually wanted is information about a Hilton hotel in Paris. Okay, now the question is how this stupid system, because I keep on telling my students that computers are stupid and they are supposed to be intelligent and computers are stupid still, so how this stupid computer could know that we meant this and not that. So if you think, if you abstract a little bit from what you know about computer systems, and you think like a regular user, and a regular user says, okay, I put it in my mobile phone, and my mobile phone knows also my calendar, and in my calendar there is a business trip to Paris in next days, and maybe my mobile phone also knows my location, and it knows that this business trip will be in a few days and I am not in Paris, okay? Or maybe I use social networks. Personally, I don't, but most of people do. And in my Facebook, I put, oh, I'm so happy I will be in Paris in next week. So these are like hints, cues for the system, and maybe the system could use it. And of course, from today's system perspective, most of these things are completely disconnected in your mobile phone. But from the user perspective, the user could say, okay, my phone knows all of it. Okay, so this is like a practical question: how you develop a system which is centered on the needs of this individual user, and that can select in a smart manner an appropriate knowledge source to, we could say, reduce uncertainty about what the user actually meant, this one or that one. Usually these systems are built in such a manner that there is this context collecting phase. Based on the context data, there are some knowledge models being built, and then there's execution of these models. And what we developed in the work with my next PhD student is a kind of feedback loop to this. So actually, while the models are executed, we collect the feedback automatically and also interactively from the user. We can adapt these models, and we also can adjust the data providers, because as I told you, we might have different data sources for this information. So for example, if you think about location, location is one of our prime examples. On high level, the concept of location can be interpreted in many ways. So to answer the questions where I am now, you could give the GPS coordinates. But on the other hand, from practical point of view, a GPS would not work in the building, so you should use something else, maybe micro-localization. But maybe the answer of coordinates is not very useful, and maybe if someone calls me like in 1 hour and asks me where I was, I could say, okay, I was in the Jagiellonian campus. And this is also an information about location, right? And users, I mean human users need different kind of different classes of answers. And to make an answer that I had a seminar in Jagiellonian, maybe I don't need the GPS information. Instead, I need my, again, calendar. Okay, so this is like a completely different knowledge source. And actually, in building of such systems, some of the main challenges regard intelligibility or understandability of these systems, robustness, adaptability, and privacy. So we argue that in a way, a user should understand to some degree how the system works, or at least the system should provide some kind of explanation, because this is especially important if the system maybe not even malfunctions, but functions in a manner which is not so obvious for the user, right? And then the user asks a question, why did you recommend this, okay? Or maybe I wanted something else, okay? And there should be a certain way of a user to tell this. Another very practical and important challenge is uncertainty about data that you are getting in such systems, especially from sensors in mobile and wearable devices, because this data can be considered uncertain from several perspectives, okay? So, for example, depending how much data you have, the interpretation of something that you thought you knew previously would change. And there is also there are at least these two classes of uncertainty from our perspective. So on one hand, there can be, there is always imprecision in your measurements, okay, this is one thing. On the other hand, in some cases, like the GPS case in the building, your specific measurement source might be not available, and then the question, and you can also interpret it somehow, or at least you should deal with it. And there are a number of this approach to deal with this, and in our work we tried to address both lack of knowledge from the sensor, a certain semantic ambiguity, how you interpret your reading, the already mentioned machine imprecision of the sensor, and of course in general the randomness of some measurements. And there is also another thing that there should be a certain adaptability to the preferences of the users, and there should be also adaptability of what the users actually mean. So actually, like last week I was in Madrid, and I would tell you that in Madrid it was cold. It would mean completely different than here in Krakow, right? There'll be also another case with temperature later on. So some changes in these systems are gradual. On the other hand, some changes in the system, like my coming back to Krakow, are quite rapid changes. And then the system should cope with these two classes of changes. Changes of context. And there's also another quite important practical requirement. So we should really consider how efficient the whole process is in terms of energy, for example, because if this is a system with constrained resources like your mobile phone with your battery, you should really take into account how much power it will use. And another important thing for the mobile users is the privacy of the data. So there are a number of ways to develop such systems, and besides the whole topic of, for example, using crypto methods to handle some things or some others, another question is, can we process in some cases the data only on your device, on your mobile device, and not just send it to the cloud, okay? So this was another requirement that we had. And we had a project on this, a PhD project, also supported by Preludium. So this is like a bigger slide about all the objective of the project. Basically, it was to address the challenges that you saw before and to develop methods for supporting the user in adapting the system, knowledge management for imperfect or incomplete context knowledge, and also this so-called mediation technique, so providing this feedback loop so the user can interact with the system. And we developed a software architecture which is based on the model view controller pattern that you might know, but we extended it so the model is adaptable, and it is adapted using different data from different context providers. So these calendar, GPS, etc. are context providers. On the other hand, in the controller part, there are mediation techniques to allow the user to be in the loop. Today in the AI, one of these, let's say, hot keywords is human in the loop, how we develop systems that interact with humans in an understandable manner. And then, of course, in many different situations, you might expect different interfaces, different ways of presenting this decision support knowledge to you. And the system should also behave in some kind of smart manner. So maybe if your mobile is for example, in your car, it should present the situation, information in the situation in different manner that I don't know, in just a lecture room. So anyway, if any of you would be interested, this is the same, I can talk about it later on, this is the same slide that you saw before with the feedback loop, but we developed some, let's say, deliverables in each of these areas. So we developed data mining techniques for adapting the models. We developed a certain knowledge model for the data that we'll have, and I will show it to you in a minute. And as I mentioned, this was supported, this was the work of my third PhD student, and the next PhD that was fortunately completed this year was actually related to collaborative knowledge engineering, because it gets also interested if you consider what happens if these knowledge bases are developed by a team of people, and there are some interesting issues. But this guy was too busy to get a preludium because he already started to work with affective computing, which will be the next part. So this is what we are doing now. So as I mentioned, for us, an important, interesting dimension of context might be affect and information about emotion. So I'm not going to make a long introduction about affective computing, because there are some experts here in the room, so hopefully you know what they've been doing. So just a glimpse about some challenges. Okay, so one of the first challenges, if you come from not from psychology, and you would expect that psychologists would give you some ready answers for the nature of emotion, is the bad news is that they don't have them. They have number of answers, and in terms of the source of emotion, of the nature of the emotions, two main ways to explain them are that emotions are cognitive, and you should focus more on the brain activity, or maybe the other group is that emotions are more bodily, and you should actually read the bodily reactions. And of course, this is not so dualistic, and probably in practice you should think about both. But then again, if you think about different measurement methods, because at the end of the day we want to do some measurements, to do some evaluation, some reasoning. So then again, there are a number of very different and very often incompatible approaches. So there might be some approaches would tell you, okay, there is a discrete set of emotions, and you can, and this set of emotions is constant for all the people, like in the Ekman model of facial expressions, or some other people would tell you that, okay, there is like a continuous multi-dimensional space, in this case two-dimensional space. There is also PAD model, pleasure, arousal, dominance would be the three-dimensional space, and your emotional condition is kind of vector in this space, okay? And you should actually calculate these values maybe from some sensor readings. And of course, this is not a new topic, and as some of you know, this topic has been around for over 20 years with after the publication of Rosalind Picard's book in 1997, Affective Computing. But we believe, and not just we, if you look at what is going on in this area, that now the technology as well as some methods progressed enough, so maybe we deliver something more than what she had in mind 20 years ago. And this is the place where we are trying to combine what you see before, so this first part in knowledge engineering, the second part in context awareness, with affective computing in the so-called ambient intelligence applications. So these applications which are somehow like integrated with your environment, maybe with your mobile phone, maybe with your intelligent car or your intelligent building. So our objective for the platform that we are developing, and this is a platform which is based on the work from the KnowMe project, are computational models of emotion, infrastructure for physiological readings, because so far we are focusing on physiological readings from, this is important, wearable devices, because we want this to work not just in the lab, but in, let's say, field applications. And as I mentioned, we are using context awareness and semantic knowledge engineering for decision support and for handling the context, the deliverables from the KnowMe project. So we are following this James-Lange approach, a little bit extended by some ideas from Jesse Prince. So basically we assume in a simplified manner that if there is some something that evokes your emotion, you will have a certain low-level perception, and this perception will result in the change of the bodily state. Okay, so this is the change of the whole body. Maybe I will jump out, maybe my pulse would change, my facial expression would change. There are a number of things that can be measured, but then in this model we assume that the perception of this bodily stage actually is after this change, and then later on it gets conceptualized. So maybe I am aware, okay, I'm afraid, and I'm afraid because there is some danger, and the snake is the source of the danger. Okay. So even if it is not entirely true, we are not discussing with psychologists about it. Assuming that at least in some cases it is true, we might explore how much far we can go with it with our work, and we assume that we can use some data mining techniques to actually detect and identify these patterns that correspond to the changes of bodily state, and what we would like also to do as to combine user feedback with evaluation of these changes. And as I mentioned, we are mostly using mobile devices. We started off with some wristbands, so the picture is still here because it is a nice picture, but these kind of devices, they are not really useful because so far, but we think the market would change, and as we don't want to invest in the hardware development, okay, we are just waiting for companies to deliver what we want, because at this moment, most of the hardware you have would not give you even soft, real-time, raw signal, okay? But we think it will change in the future. So actually we backtracked to a number of devices which are much more powerful in terms of reading. You can still, with some, let's say, imagination and basic skills, you can still build a wearable device with it, okay? Maybe not so comfortable as a wristband, but still wearable. And actually this is 10 times cheaper than this one, okay? But this one comes from MIT, so probably you pay for the label, MIT label. Anyway, but what is important are these are wearable, and we are in our work we are adapting this framework that you saw before for the detection of emotion, of the change that would correspond to an emotion, identification and classification of this emotional condition, and then what is important, we would like to integrate this information about emotion with what you've seen before. So maybe this Paris Hilton thing, okay? This kind of situations. And for collecting context data from mobile devices, we are using a framework, a ready framework that developed in a PhD in, I think, Iceland. I can't remember exactly where, but anyway, this project is quite mature. It's called Aware. And what is nice is that they consider sensing on a more general level. So a sensor may be your accelerometer in your mobile, but a person can also be a sensor. So asking a person or asking harvesting the Twitter account of a person is still getting information from the sensor. And this information can be acquired from many sources and then stored in both cloud infrastructure as well as on your mobile, which is useful for us. And basically it handles sensing, processing, sharing of the context knowledge, as well as connections with some other applications. And they also solve some of the practical things, like, for example, how to query your sensors not to kill the battery of your phone. Okay, so this is like low-level engineering work that we didn't want to do. But what we would like to get, so this is like a, let's say, wishful thinking slide at this point, and very much simplified. Okay, so imagine that first of all, so you have some context information which is now easily available, maybe from your calendar, maybe from your weather information provider, and once we have it properly integrated, maybe you have some readings about your heart rate or galvanic skin response, and then we would like to predict how some change here would affect some change here. Okay, so this is like and this would be useful for our decision making. So this is a point that we would like to get, hopefully soon. But another thing is, coming back to my Madrid example, is that certain concepts may mean different things to different people, but also a very important thing here is that the kind of machine learning methods we are using, they are referred to as incremental machine learning or learning from data streams. And this is a different approach for building machine learning models. And in this case, a very important challenge is so-called concept drift. So basically, my concept of considering, for example, global warming, my concept of cold winter in Krakow would correspond to different temperature readings today than to what I remember when I was a kid, okay, what it meant to have a cold winter in Krakow. We developed a number of extensions for this rule-based language that you saw at the beginning of the talk to handle this. So, for example, we have these time-based operators and statistical operators in our rules. And another thing is that we have certainty factors regarding each of these rules, so we can assess certainty of some decision making. And another thing is that in order to learn these rules from data and in order to update these rules from data, we used the, if you know about incremental machine learning, if you remember the classic decision tree learning like ID3 algorithm for decision tree learning, in incremental machine learning there is a group of algorithms which are called Hovding tree algorithms, so they are able to update your decision tree with the data stream, and what we developed is an extension that adds certainty factors to the branches of the tree, because as you remember we want to address the uncertainty of the readings from the sensors, and from the decision trees we are transitioning to decision tables, and then we can get these models that you saw at the very beginning in the forms of tables. And as you can see, all of these rules here, I mean the decision part of the rule, have certainty factors, okay? And the whole framework in terms of the reasoning engine, it's developed in Java and it runs on your mobile phone. So in a way, probably it is still the only rule-based engine that runs on a mobile phone in a, let's say, sensible manner. And this work, together with the affective computing part, was published in several journals in last 2 or 3 years. And now we are thinking about, as on one hand it is basic research, as you can see here, but on the other hand we still want to be as close as possible to some future applications, and we are also thinking about working with some companies at some point if possible. One of our recent use cases has been in affective gaming, and this is a thing that we are cooperating with Paweł Węgrzyn and Jana Gasiński here. So you might know that affective gaming is concerned with developing special kind of games that evoke emotions and address the evoking of emotions and take emotions of a player into account during the gameplay, and maybe adapt to the emotions of the player. What we would like to develop is a new kind of the so-called affective loop, so a special kind of adaptation to the players. So in affective loop, we consider this case when the game elicit emotions in you. You have some emotional responses in the game, and then the game engine would detect these emotions, it would classify them, and then the gameplay in a very general sense would change. Okay, so the player has an impression that the game reacts and adapts to her or his emotional condition. And on one hand, it is a very interesting from the conceptual, basic research point of view, and on the other hand, I don't have to persuade you that it's very important from applied research point of view and some cooperation with the industry. In fact, you can think of the game characters' emotions, so NPC emotions. You can think about player emotions, and you can also think how you design these games. If you know from the very beginning that you would be able to address this and this, the question is how do you design such a game in a different manner? And actually our focus, ultimately I will focus with my next PhD student is actually on the game design methods. And for this, on one hand, you need a special kind of technology, so some of these devices that you saw before can be used, and there are some companies like, for example, Intel that develops special sensors architecture that can be used and is being used for affective games. And you also have some prototypes already, but very limited. Most of them are, let's say, incomparable to each other because they have a completely different design assumptions. And some of them are just like described in the papers, whereas some other, like the Nevermind that you see before, you can get it on Steam, you can connect to it different devices, and you might have some, let's say, impressions about affective gaming. So what we would like to do with that PhD student is actually, as I mentioned, focus on design patterns in games, and this is the work that we started with Jan. So we are considering affective game design patterns. So they follow this idea from patterns in game design from Björk and Holopainen. They propose quite a large set of certain repeated patterns that can be identified in how the games are designed, different classes of games. The bad news is that from the game studies perspective, it has never been continued later on as we discovered, but now we are investigating how these ideas could be actually used, of course in some limited scope, in the design of games, assuming that you have all this nice hardware and all this framework that somehow identifies the emotions of the player. And what we presented this summer in IEEE GEM conference is an early let's say, idea of this design process. So how developers could use this information to model the game in such a way that the gaming experience would be adapted. So this is quite early work, but I hope it will develop nicely. Also, before that work, we started with Barbara, so that PhD student. This was also the work with Jan. We had some very basic game prototype, like a scroll shooter that was in a very basic manner detecting the emotions of a player. So for example, if you got hit by something, your timer would reduce, and then would people get upset, and there are a number of these patterns identified here. Actually, also this summer on the AfCAI conference, we demonstrated another prototype, which is already based on Vitalino, and it is in Unity, because the other one was not in Unity. We would like to use Unity where possible, because it is a kind of standard tool. The players could play this game, and the game would detect the changes in heart rate and galvanic skin response. And it was actually quite nice. We even get some award for it, and people were really enjoying it, and people really had this impression that the game understands their emotions, whereas from our point of view it was really kind of fake. Okay, there were a number of tricks, but it is still important to see, as this is a very complex phenomena, what is the let's say the border between some basic tricks that you can make to have the impression of the player and the real interpretation of emotional conditions. So here we still focused on heart rate, galvanic skin response, but also on the muscle reaction. So this is like a low-level work. So the other one in design is like a high-level work, and this is a low-level work, and we hope that these two will meet at some point. And now coming back to knowledge engineering and slowly coming to the end of the talk, the thing is that even though we are now focusing on all this data acquisition from number of sensors and data-driven processing for knowledge base updating and adaptation, somehow we still need this conceptual description of the system. There is still room for knowledge representation. And what for? For example, for communicating with the user. Okay, so we mostly communicate on a conceptual level, not on level of raw numbers. At some point, users could ask some questions, as I mentioned, why the system proposed this or that, and then the system cannot be a black box solution that would answer because, right? The answer is 3, or if you remember Hitchhiker's Guide for Galaxy, the meaning of light is 42, if I remember correctly, right? But it's not really a meaning from our perspective. And for personalization of a system, so if people say, I like this and that, these are usually not just numbers. There are some concepts that need to be translated into the answer to some numbers. So there is still room for combining knowledge engineering that is tied closely to data interpretation. And the last part that was advertised in the title is the understandability and explainability of AI systems. And I will not talk about it very long, but I wanted to tell you what it is about, because right now it is a quite important topic. So there's this abbreviation XAI, so explainable AI. So basically there's this argument that some of the models that we are using in AI, most commonly different neural network architectures, but not only, they are more or less black box models, right? We have huge amount of data, we train them, sometimes they operate brilliantly, but sometimes they don't. And most importantly, we cannot, if we get some answer from such a model, we cannot ask the question, why? Why this answer and not some other answer? And if this model is wrong, we cannot ask the question, why it is wrong? What failed? Then we really need to investigate the whole learning process, the data sets that we use, etc., etc. And this is especially important in some applications of AI, like medicine or law, right? And this is why explainability is quite important right now, and this so-called human interpretability of the system. Okay, so maybe it doesn't mean that the regular user should be able to understand how the system works or how the system operates, but at least there should be some people who are able to do it, right? And then with some of the models, it's just a black box, and no one can explain why the system failed. And this is also related to this. When we are writing projects, there is this paragraph about societal issues. And this is really quite important these days, because these systems are penetrating the society. And this question about explainability and transparency of AI systems also comes back to comes down to the question of trust. How much people accept these systems, how much people trust these systems. And right now there's huge discussion about it, huge debate about it, and definitely this cannot be just left to scientists, just engineers. And IEEE, which is a quite important organization in electrical engineering, and this is, I mean, computer science and AI is partially considering this, published already a second version of the so-called ethically aligned design document. It addresses a number of other topics. Mostly the focus is on ethics, but this is very much related to, I mean, explainability contributes to this ethical analysis, and I'm not going to discuss it because it's a different topic. But if you are interested in this, I would strongly advise you to go to the web page, get this document. The first version was quite short. The second version is already like 120 pages, and there are different chapters that were consulted with some domain specialists. And again, there's a lot of debate about it. And there is also, I cut out the slide, but there is this last year they had this Asilomar conference in California, where they had this Asilomar rules for good artificial intelligence and what it all means. Okay, and there is so there is a lot of I would say just fuss about it, but there is a lot important issues into it, and I think for the social acceptance of this system, it is quite critical. And in this area, besides working in just, let's say, purely AI workshops, I started cooperations with some of my colleagues from the Jagiellonian, actually from the law department, the theory of law department. And in 2 weeks we'll have a workshop on a pretty interesting conference, because URIX is a conference of lawyers working with artificial intelligence systems. And this conference has been around for, I think, 23 or 25 years. So it is very much established conference, and the use of AI in legal domain, maybe not in our country, but in some other countries, is a quite important topic for many years. And this is why we are we propose this workshop on explainable AI to work with people from law, because after working for so many years in the Institute of Philosophy, I decided, okay, I can have some coffee with the philosophers and discuss with them, but it is not so useful. And I really prefer to talk to the lawyers, because at the end of the day, what matters are the legal regulations that would conceptualize it. They would still use some ethical concepts, so philosophical context, but I still prefer the lawyers, especially that they do some kind of logical reasoning, at least on some level. So we hope it will be just the first edition of the workshop. We hope that the workshop will develop. Okay, so as you could see, there are a number of ideas in this talk and in this work, which somehow is like a compressed presentation of many things that we've been doing in last years. Right now, these topics of explainability and affective computing and human-like AI are most interesting for us. And of course, it's a very complicated area, and we do know that we don't have a lot of strong results at this point, but we hope it will get better. And on the other hand, we really try to distance ourselves a little bit from this work. And my message on my recent talk is that if people ask me if I'm afraid of artificial intelligence, I'm telling them I'm really worried about natural stupidity, because it's much more dangerous, and we should work on ourselves in a smarter way before blaming artificial intelligence systems. Thank you very much for your attention.
Thank you very much. We have time for questions now. Well, maybe I will start. To what extent do you think it's realistic that there would be some sort of a global legal system regulating artificial intelligence? Because there would be, there are many systems that you could think about some hostile artificial intelligence. So, to what extent it's idealistic view, and to what extent you expect that there might be some strict legal regulations?
I definitely think there will be legal regulations about the design of such systems. I hope there will be no global system being developed, but the technology is there. Actually, if you think about China and the Chinese social score system, which like last week I talked to some people from China, and they said, well, it's pretty much widespread already. You are still invited from Europe to go to China, and we don't include you in the system, but somehow we are including most of the Chinese, and it's working pretty nice. And I think there might be this idea to implement this kind of system for controlling how people travel, actually, because right now most of the system on the airports are actually being converted to the kind of systems that only use AI methods for biometric identification, classification of people. This explainable AI is a nice topic in the US, because they already implemented a number of these systems, and they had many problems with systems identifying terrorists, right, or possible terrorists. If you remember a book from Philip K. Dick, Minority Report, there was also a movie. We already have this kind of thing, but not with precogs. We have it with the AI, right? So AI is right now being used to profile people who are terrorists or potential terrorists. So I think from security would be a nice excuse to use it. I hope not on a global scale, but maybe in some countries like the US or now maybe the UK. So
there's this case of I think Colombia, who introduced a citizen card, which is collecting practically all the information, including medical, financial, and if you don't have such a citizen card, you may have problems even arranging simple legal not as I know, getting coupons or because the prices. So this is a way of really forcing people to voluntarily provide all the information.
Yeah, I think a very important thing is what is the use of the data and what is the scope of the use of personal data. And this is much more basic than just AI itself. But the tendency is that people actually want to give away their data because they enjoy all these nice features of systems, and some people really enjoy giving up their freedom for the promise of security, right? And politicians really like promising security, so there's a risk. There was also another question.
So, if I understood your approach correctly, you are mostly interested in expert systems. Right?
You could use the name of expert system as a decision support system, but these days it's very much different. But the idea is similar, of course.
From the plan when we talk, I actually got the impression that the question I thought you would answer would be how to integrate neural networks with expert systems, aid them or support them in and ultimately explain them, right?
This is another thing. I mean, if you consider explainability in AI, one of the way to work on explainability these days is how to generate symbolic models from neural networks. But this is not actually about integrating them. One way is to just build neural networks and then to demonstrate how you somehow extract some knowledge to build an explainable model. There are some other approaches how you design a neural network already having this model in mind. Okay, so for example, they are generating decision trees from neural networks. I don't really care if we use expert systems or if we use neural networks, because I think the lessons that we learn, that we should learn from AI, I mean, AI is already over 60 years old, right? Is that there is no silver bullet. I mean, you cannot, at some stage people thought, okay, let's use all these good old-fashioned methods only. Then there was a switch to neural networks, then there was a backtracking to semantic networks. Now, of course, it's all about deep learning, right? But I think, I mean, it's already bouncing. It's already bouncing back from deep learning to these symbolic methods. And I think the lessons learned is that it's not about a specific method, it's about your requirements and expectations of the system. So answering your question, no, I don't really care about integrating rule-based systems with neural networks, and I don't really think it makes sense. I mean, neural networks are splendid for doing some things from the data, and we should use them. Rule-based systems are incredible for doing some other things, but the main trick is how you build a hybrid system that can use maybe both, or maybe can switch from, maybe in some cases a hidden Markov model is much better for interpreting your data stream than your neural network, and maybe your system should be able to switch. I think humans are also switching to a completely different sensor types, reasoning types, and I think this is what AI systems today lack.
What of the projects that you mentioned were hybrid, usually? Were all of them? Or?
You mean with this kind of hybrid approaches? We don't have a project now, okay? We are, I know some teams who, I mean, we are in contact with teams who are developing or aiming at developing similar things, or for example, a team from Tilburg, they would coin this term of explanation-aware computing, where they would build from scratch, they would build a system in such a way that the system would be able to generate, using very different solutions, generate explanation of operations. So, and for it was especially important in the medical domain, because at each point the doctors wanted to ask this question, why? Okay, so there is no ready solution for this. It's work in progress.
maybe not really that related question to you, but do you know why expert systems fail for medical applications? I mean, one would naively think that, the only thing that the doctor makes is to, follow the decision trees. Almost the medical books, almost all the medical books look like decision trees, right? Why do expert systems why don't the expert system support the doctors?
I could answer in two ways. The first way is it's like this official way that building and maintaining the knowledge bases in expert systems was expensive in a way and difficult, and especially adapting the knowledge base if you didn't have some machine learning techniques. Adapting the knowledge base, extending the knowledge base was costly. Okay, so this was like a practical question. I mean, the practical answer. But I could also tell you, they are used, very much used. I mean, I could refer to some of my colleagues in Germany, and they would develop splendid expert system. They would usually not call them expert systems, because if you call something an expert system these days, I mean, they would tell you, okay, this is like a technology from the 80s, so this is why we call them business rules, we call them decision support systems, but these technologies are very much being used. Maybe we don't publish it, like in books, but...
So for cancer-related decisions and so on, there are some such systems that I know of, but for example, I would imagine that you would have a general system that people could use as a first, for first care. Before you go to a specific doctor, you would like to get pre-diagnosed to know into which direction go if you have any illness.
There are such solutions, but not on a global scale.
Yeah,
so
it's not exactly clear to me why we don't know of any such solution that would be good enough to just go to.
So again, two answers. I think first answer is that so far the progress of AI was about making really smaller and doable things, and we are making a lot of progress because of these restrictions, okay? So this is why our chess playing systems have nothing to do with autonomous cars, right? We use completely different methods in different applications, and this is why we stopped developing general systems, general languages, because all of these things, I mean, these are nice. Sometimes it is nice to get a big EU project promising this, but everyone knows it will be a failed project in a way, I mean, not officially. But then another thing is that there is a very much difference if you think about these technology readiness levels. There is a huge difference between developing something on TRL 4 or 5 and something on level 9, even though in Polish projects we very often say that this is level 9, but it's not, and to get it implemented in the full scale. But if you think, for example, about systems, I don't know about medical domain, but the systems that they have for e-government in Estonia. And there are some, if you're asking about medical systems, I do know about the systems that were used on a, let's say, much smaller scale, maybe not the scale of a country, okay, but in the scale of some village or a city. So it's more of a financial, political decision. It's more about the trust of the people, etc. With this kind of system, it's not a matter of technology. The technology is there. I mean, we already have technologies for many things. It's just about making a decision and an investment.
Remind that there's a problem that we often teach the system based on our data. So these data often contain some bias, some racial bias. So the general problem that this system strengthen these biases, like in prisons in the US. Without discussion, explainability help you that.
You mean the problem of bias in
the data which are learned by the system and used as part of it?
So actually these biases are one of the arguments against these black box systems, okay? And this is one of the arguments for explainability, because right now we have number of publications that demonstrate how harmful this bias is, and I think it's also like this curse of big data. The bigger your data is, the more difficult might be to identify your bias. And this is why I mean it's a common thing. If you're using specific machine learning methods, they might be sensitive to bias in your learning. And there are a number of cases, I have it on some other slides, for example, these cases when some of the chatbots built by Microsoft got really biased, racist, etc. And then no one knew why, and they would, let's say, defend themselves like, okay, we used state-of-the-art methods, and then we used state-of-the-art data set. And there was a nice paper in some really top journal, maybe even Nature, I'm not sure, I can give you a reference, where they did a very large and costly study of the data set, why that was used to train the bots. And the answer was so obvious. This somehow balanced data set of different statements from people was biased. And the answer was, and this is again some slide that I have in some other place, because it's quite interesting for me, because for me this would be an argument that an AI system is human-like, because the answer was, well, humans are, you could say sometimes, but humans are sexist and racist. And then once we build a system which is so much human-like, we say, oh, no, we don't like it. We want it to be perfect. And then the next step is, okay, so what this perfect, ethically perfect AI systems would do with the humans, and this is the point where we get afraid, like, maybe they will wipe out the planet. So this is, we are not addressing this directly here, okay, but this is why this explainability issue is being raised, to also being able to expose and maybe explain this bias, because it's, again, it's like a curse in a way.
But actually, in case of this chatbot, it was a really matter of the data set, or was it the case when this chatbot was supposed to learn from the interactions?
Both. Yes, you are right.
And then this meant that they didn't control the data set because they didn't control what people fed this chatbot.
Okay, they had several prototypes, and in that paper that I read, they argued that there was a bias in the data set, but of course the other idea was that you have this human in the loop and you got the interaction, and the interaction is like amplification of certain threads that you already had there. But then there was this question, okay, so what you are supposed to build into this boat? Some kind of ethics of not being racist or sexist, and this is when it becomes interesting. But it happened to them in at least 2 prototypes, and one, I think at least one was more about the bias in the data set. But yes, there are some cases when if you feed enough hate posts into the chatbot, it will just, if it is a stupid ELIZA kind of bot that will develop its knowledge base and responses, that it will just process your hate speech. But then again, it would demonstrate that humans are biased in a way that some other humans don't like or don't approve.
I have some doubts about the glass box philosophy, and I will give you an argument. Just 2 days ago, I wanted to make a picture of our servers for some kind of advertisement-like reasons. And then people at the center told me that they want to look at the pictures, because if on the pictures the name of the company which is producing, which has produced our servers would be made public, this would be already a serious hint how to attack our system. So the name of the company of our server is actually a secret. Okay, and you don't. So if you think about the glass box philosophy, it means that one could, in principle, knowing the architecture and the reason why the artificial intelligence is giving such and such answer, one could think about designing some, I don't know, malicious software which would lead to, I don't know, adversarial examples, etc., etc. So, for me, this, I understand the philosophy, but it looks extremely idealistic and utopian.
I think that the argument here with explainability is more about being able to get an explanation, and it doesn't mean that you must always have a glass box for everyone. Because even with affective computing, our colleagues in Sweden, they recently wrote this nice paper. I can't remember the name of the conference, but there was a special session inspired by the Black Mirror series. And they wrote this provocative paper, how the world would look like if you would have in your phone the technology that could allow to get the emotions of everyone around you, right? And then there is this question of privacy and if you want to do it, etc. But here the argument is more about not relying only on black box models, or basically being able to have models that could provide explanation, at least maybe to the designers or maybe to the owners or whatever. It doesn't mean that everyone should be able to get it, and actually most people would still not understand, right, some of the systems. So it's just about being able. It doesn't mean we must have it.
So I think.
Thank you very much.